Okay, so right, so the context for this talk is end-to-end encrypted messaging. So for our purposes, we can imagine, these types of services like Signal and WhatsApp and others that we've heard about in other talks and in research before that, that arrange to share a secret key between a sender and a receiver, and use that secret key to encrypt messages in a way that the service provider can't read the content or modify it. So we get this nice end-to-end security guarantee. And as I mentioned, these are quite popular now, right? Which for this audience probably goes without saying. We have billions of people relying on these for good confidentiality, privacy, and other types of security properties every day. There's been a lot of work on how to just do this basic functionality of getting the end-to-end kind of confidentiality and authenticity guarantees. And I just listed some of the earlier work, and there's been a lot of more interesting work, including some of the talks at this workshop on how to do that. For the purpose of this talk, we'll just kind of boil it down to the simple idea that we somehow share in a good way a secret key, and then we encrypt with a symmetric authenticating encryption scheme the message, and that key for that authenticating encryption is not given to the service provider. Okay, so while we get this amazing confidentiality and authenticity guarantees, one issue that is complicated actually by end-to-end encryption is when providers of messaging services want to help users with abuse. So inevitably, we'll have some users sending kind of horrible content to other recipients. And we may want to enable features where the recipient of abusive material can report it to the service provider so that the service provider can then judge whether this was actually violates kind of community principles or other policies and take action such as kicking a user from the network or some other types of mitigations. Now, the problem with end-to-end encryption in this context is that the provider can't verify that this was actually the message that was sent because they didn't see the encrypted content. And so this raises a bunch of questions about what we should be doing here. Could the recipient frame a user by saying that they said something that they in fact did not send, etc. So this problem was recognized quite a number of years ago now by Facebook when they were building their secret messages feature for Facebook Messenger. And they even came up with a very interesting approach called message franking that would enable the recipient of a message to give basically a cryptographic proof of the message contents that they're reporting, so the service provider could know that they were reporting a legitimately sent message and then judge its content. So in this talk, basically that was our launching off point for this line of work that we've been doing over the last few years, trying to explore these types of cryptographic tools that enable content-based moderation in end-to-end encrypted messaging. And what I'll talk about at a very high level is some of our work on understanding the Facebook message franking approach and how to abstract out kind of cryptographic goal that was implicit in their work and make that a first order kind of design target for symmetric encryption and authenticating encryption schemes. And then I'll talk about our extensions of this. And in so doing, we'll also point out a vulnerability that we found in Facebook's message franking system. And then I'll talk about some extensions trying to deal with limitations of message franking in terms of settings where, for example, we have some type of anonymity properties where asymmetric message franking, a new primitive that we came up with, might help, as well as dealing with things like trying to trace the source of, say, a viral messaging campaign in an end-to-end encrypted system. So let me just go over Facebook's message franking protocol to provide some background, and then I'll lead up to showing the vulnerability that we discovered in how Facebook particularly was handling attachments. Excuse me. So what Facebook did was encrypt not only the message using this authenticating encryption scheme, but also a key for a cryptographic commitment to the message. And then that commitment, which ends up being a keyed hash of the message, in particular HMAC, sends that on the wire so that the service provider can see it. Now, because KB is hidden underneath the authentic encryption, the provider doesn't learn information about the message when it sees the commitment C sub B. But it can MAC that value or digitally sign it so that it can assure later on that it knows that it saw this actual commitment value going by. The receiver, when they get this whole bundle of stuff, they can decrypt it, recover K sub B, and use it to verify that the commitment C sub B is matches the message that they saw. Now, to report abuse, the recipient can then send this value, K sub B, the opening of this commitment, the message, the commitment value, as well as this symmetric signature, the MAC T sub FB, back to the service provider. And the service provider can then verify in turn the commitment C sub B, that in fact this matches the message that is being reported by the recipient, as well as that they in fact saw this commitment C sub B previously by checking this symmetric MAC T sub FB. And with all that, the provider is now convinced that indeed this sender sent this message, and the message contents were in fact this illicit content. Now, attachments are handled differently, and I'll explain that in a moment. So this was really interesting and a new type of application of authentic encryption plus commitments, but it raised lots of open questions when we saw the white paper that Facebook nicely released publicly. You know, one, what is the security of this approach? Can we kind of formally analyze it and understand its various security properties? What does security even mean here? They had some informal security goals, but it would be nice to formalize those goals to facilitate analysis. It would seem like there's maybe an abstraction here if there's a new type of cryptographic primitive that's actually being sought that they're achieving via this combination of encryption plus a commitment, and maybe we should abstract out what is that actual technical goal. And of course, are there faster or otherwise improved approaches on their initial design? So the quick answers for these is the approach is actually secure as I've described now. It's quite fine, but the extension that they use to extend to deal with larger file attachments like images or videos is not secure, and I'll describe that in a moment. And then we went on to provide some formal abstractions for what is this cryptographic goal and try to put it on a firmer foundational footing so that we could provide improved schemes. So let's just start with the attachment issue. But before we can describe kind of the problem, let me just go over what are some of the security goals that we want for this message franking type setting, and which I've alluded to already, but just to go over again. One is what we call receiver binding, and this is what I mentioned previously, that receivers shouldn't be able to frame a sender as having sent a message that they in fact did not send. So they're bound to the actual message that they're opening, is the only one that only the message that was actually sent can they open and convince the provider was sent. We also want a symmetric or complementary property called sender binding, that a sender can't send a message that is received and kind of read by the recipient, but which can't be reported. Excuse me. This would mean that they could send abusive content that couldn't be moderated. There's also other guarantees where we want the confidentiality and authenticity that we target in general for end-to-end encryption to be maintained for all the messages that are not reported. And we also additionally want deniability, the idea that whatever we do here shouldn't really be useful to prove to third parties, to other people, messages that were sent by a particular sender. So you can't use this as cryptographic evidence to implicate some people as sending particular messages. So in our analysis, we show that the Facebook scheme achieves these goals, but not for the extension to attachments. And the particular problem for attachments is that we showed an attack against sender binding. So a sender could send illicit content that wouldn't be reportable. So I was going to go over what the issue was. Excuse me. Sorry about that coughing. So the extension to attachments that Facebook used works as follows. Instead of just applying the message commitment and encryption directly to attachments like images or other files, what they would do is use the protocol as described so far, but for encryption key, K file in this diagram, that's then used to encrypt the file contents with a fast AES-GCM authenticating encryption. And then when you receive, you verify that the commitment C sub B is correct for K file. And then if that's true, then decrypt the file and show it to the user. And what this means, though, is that there's a gap between the encryption that's being used and the commitment that's being used for the key, K file, and for the actual file contents. When you report, and we'll get back, that's important, we'll get back to that and exploit that in the attack in a moment. So to report abuse, the receiver kind of opens K file as before, and other recent messages actually at the same time. And Facebook ends up checking the openings and then decrypts all unique AES-GCM ciphertexts that are submitted in this report. So they actually bundle all the recent submissions sent, and we'll just look for ciphertext that are attachments and then decrypt them and put them in the report. So, and this just shows an example where, okay, now we have two files, say, that get sent back to back by the sender. And when you actually do a report for either of these attachments, say, or the receiver will send all of the commitment openings and content information back to the service provider. Okay, importantly, I emphasize unique here. One thing that they do is, as presumably was for efficiency reasons, they would only check, they would basically go through these file attachments and only decrypt new ones that they saw. If they saw a repeat ciphertext attachment, they wouldn't decrypt and use it. And this, at first glance, seems like it's fine as an efficiency improvement. But what we show how to do is exploit AES-GCM, and in particular, show a malicious sender that can build specially constructed ciphertexts, ciphertext, a single ciphertext, that decrypts under two different keys. So one key, K sub file, decrypts this particular ciphertext to an innocuous image, and another key, K file 2, decrypts it to an abusive image. And the point being that, excuse me, because we can arrange for it to be the same ciphertext, when the abuse report occurs, only one of the two images, and if you do it in the right order, the only innocuous image will end up in the abuse report, and the other one will essentially disappear and be invisible to the moderation system. Excuse me. What's interesting about the attack is it doesn't exploit anything with the basic commitments and that are used for the keys. Those are all valid and verified correctly everywhere. And it's really the gap in using this key, K file, to then be used with a insecure, in this context, authenticating encryption scheme AES-GCM. So we are able to do this. I'm not going to go into the details of how to build this ciphertext in the interest of time. It's kind of an interesting way of exploiting the structure of AES-GCM in terms of how it uses universal hashing-based message authentication as opposed to something like HMAC, but there's a bunch of details. At a high level, of course, this may seem surprising. AES-GCM is one of our most widely used and thought to be secure authentication encryption schemes, and indeed it is secure in the context for which it was designed. The point is here that we have a very non-standard attack setting where the attacker gets to choose the keys, right? And so they can do some special computation that takes advantage of their ability to choose the keys themselves. In most uses of AES-GCM, you're in a threat model where the key is honestly chosen and held secret from the adversary. And for the cryptographers in the audience, this comes back to an issue, which is that AES-GCM is not what's called committing, or sometimes called robust. It's not robust, which is just the formalism that has been explored in a number of previous papers showing, describing settings where you don't want an adversary to be able to find a single ciphertext that decrypts properly under 2 different keys. Okay, so ultimately what we're able to do is build a kind of proof of concept showing how to have a single ciphertext that decrypts validly under AES-GCM to 2 different images. And we use for these images as example, kind of a cute kitten and this salamander, which is an axolotl, which is an endangered salamander species. And I guess the pun here is that Facebook Messenger was using, the stability Hellman ratcheting, which is called axolotl, and they ended up referring in their source code to encrypted messages as salamanders, and hence at risk of explaining a joke and therefore killing it. That's why we're worried about invisible salamanders that aren't visible to the moderation system. So we worked with Facebook to understand some of the details of the attack in terms of how it would work on their systems, and really appreciate the secure messaging team, particularly John Milliken, for answering many questions and helping us with the responsible disclosures so they could fix the problem. So coming back to like, what's the kind of root cryptographic issues here? Well, what we thought about is like, oh, actually we should abstract out this goal, right? There seems to be a broader primitive here that message franking is building in this particular case using standard authenticating encryption plus commitments. And what we thought was like, it might be better to start from first principles saying, okay, what is the cryptographic primitive that we need here, and try to include all the functionality and security properties right away in the abstraction that we're targeting that are needed for this type of message franking application. And so we introduced this formalization in the Crypto 2017 paper and referred to as compactly committing authenticating encryption. The committing referring to the fact that we want these types of robustness properties from our authenticating encryption, and the compact referring to some efficiency goals that come up there. And again, in the interest of time, I'm not going to go into details about this and just refer you to the paper for more details. We have done an exploration, kind of how to build these compactly committing authenticating encryption schemes. First, looking actually, can we repurpose existing authenticating encryption schemes in a more or less direct way to serve as committing authenticating encryption? And it turns out even there's some subtleties. For one, things like AES-GCM, we actually already demonstrated don't work via the attack I mentioned before. But even for schemes that we think of as should be providing the committing properties like encrypt and HMAC, you have to be a little careful. There's subtleties, right? If you use 2 different keys, for example, a separate key for encryption and a separate key for HMAC that are independently chosen, then that ends up not satisfying our security goals. We also introduced new schemes that provide performance improvements over the kind of existing constructions like Facebook's. And kind of the high level takeaway from all this is that, if you had used these secure CCAE schemes for all of the components of symmetric encryption in, say, the secret messenger application, then it would have prevented our attack, and this would have gotten rid of the root cryptographic vulnerability that our attack exploited. Okay, so, excuse me. What I'm going to do now is switch gears and talk now a little bit about some of the limitations of message franking, even if you start using CCAE type constructions that avoid those pitfalls that we highlighted in the attack against the attachment franking that Facebook uses, and which also spawned some interesting kind of new directions for how to help build cryptographic tools for moderation settings. So the first limitation, which I'll talk about and our work on addressing, is the fact that message franking is explicitly designed for a setting where the identities of the sender and recipient are known to the service provider. So the message contents are secret, but the identities are known, which was the case for Facebook's secret messenger feature, for example. And then the second limitation I'll talk about is that message franking just kind of provides a one-hop kind of thing where a recipient can say, oh, I received this message from this party, but in certain type of abuse scenarios like viral message forwarding campaigns where you have some user that's like forwarding or that's sending out content and then that gets forwarded to other people, this message franking may not be sufficient to really track down the source of a of this type of abusive content and therefore limits the mitigations that a provider could put in place. So I'll talk about these in a bit more detail, and again, just pretty high level overview of our approaches to building cryptographic tools that support eliminating limitations in settings where they arise. So for message franking, the first limitation is this issue of the fact that the service provider really needs to know the identities. And that was made explicit a bunch of slides ago, but to remind, the point is that when Facebook generates, for example, these tags that sign the commitments, they actually do it also with the sender and receiver IDs. And that binds this report that is sent and the content that's confirmed to the actual sender and recipient identifiers. But that fundamentally requires the service provider knows the sender and receiver when they actually make those tags. And so for systems like sealed sender or signal with sealed sender, which is a feature that provides sender anonymity, which means that the service provider doesn't actually know who the sender is of a particular encrypted message. Well, in that type of setting, if you wanted to build message franking style tooling, you wouldn't be able to using the techniques we've seen thus far. So what we started looking at was like, okay, can we extend this idea of message franking to an asymmetric setting, which means in particular, instead of just relying on symmetric keys, like what was done with the message franking so far, we actually allow all the users for the message franking portion of the cryptographic protocol to have a public key secret key pair. And use this now to try to provide some accountability about messages that are sent. So a very simple example is to use basic digital signatures. So the idea being that the sender can sign the message they're sending, include the signature inside the encryption that's being used, the end-to-end encryption that's being used for sending the message. And the recipient can verify that signature. And then if they want to report abuse, they can report that signature as well as the message content, and the service provider can verify the digital signature as well, and then be confirmed about the message content. So in fact, this achieves sender and receiver binding. It actually achieves the accountability goals we want. It would be an easy solution. But one thing it doesn't provide for us is the type of deniability goals that Facebook and others target in this context. In particular, because now, a malicious receiver could just publish somewhere on the internet, this message, this digital signature, and the public key that's bound to the sender, and anyone else would be now convinced cryptographically that the sender had in fact sent this message. So we had to go back and think about, okay, can we build digital signature type variants that provide the types of guarantees that we want in terms of accountability, but also provide some type of deniability notion. And that's where this idea of asymmetric message franking schemes came from. Now, the key challenge here is that we want to build, basically a signature scheme that somehow balances the deniability goals, meaning that to third parties, you should be able to forge, legitimate looking AMF signatures. But to the verifier, as well as the service provider, these can be linked to the actual sender identity. And one of the key challenges, we really need something where the receiver can verify the signature and verify that the service provider will be able to verify it. The latter being important because if you didn't have that property, then you wouldn't be able to achieve sender binding and potentially send a kind of malformed signature that the recipient thinks is fine, but then the service provider will reject as not valid. So in this setting, we end up using variants of what are called designated verifier signatures. The signing operation now takes not only the secret key, but also the public key of the recipient, and then the complement of that when you're verifying. And then there's a special verification procedure that works with just the public keys of the participants that the service provider can use. And the point now is that we will also be able to say that the deniability will be achieved because we'll be able to show for our constructions that the recipient could have generated a valid-looking, public message signature pair that was not in fact sent by the sender. And that actually is true even if they want to go so far as revealing their own secret key. This will still be something they could just generate a valid-looking secret signature, and it could have been something they just generated and not something that was sent by an actual sender. And so this provides some cryptographic deniability. So our starting point for constructions was designated verifier signatures, which are an old idea back from the mid-90s that allow you to kind of designate who's going to verify a signature. But the key challenge here was extending it to this kind of three-party setting in some sense where you have the recipient as well as the provider who needs to be able to verify in different ways. Turns out you can do that by building a designated recipient as a verifier of a proof that the signature to the moderator will succeed. And you can do all this with Sigma protocol-based zero-knowledge proofs. And it's even practical to deploy, at least from our perspective. You get 489-byte signatures, and they take just under 10 milliseconds to generate signatures. Okay, with that, I'm going to move on to the last topic, and then I'll wrap up and take questions. So remember, the second limitation was that we can't really deal with forwarded abuse content in a way that allows the moderation service run by the service provider to detect who was the original source of information. And viral misinformation campaigns are are a pretty big deal on encrypted messaging platforms. So if you imagine that this one communication sent from a recipient sender to recipient is just one link in a graph of message flows. And perhaps this particular thing, this information that, the election was canceled, right, which is some misinformation, was actually a part of a campaign by some source that is sending these in mass and trying to get them forwarded by people. So yeah, not a hypothetical issue. In fact, something that has had lots of problems, particularly on WhatsApp, faced a lot of these viral misinformation campaigns, both related to elections as well as other rumors that led to violence and other issues. And it's something that we would really like to have moderation tools that can help us combat. So the issue here, that if you think of in our message franking style schemes, either AMFs or regular symmetric message franking, if you have a downstream recipient report this abuse message, that'll kind of reveal this one link in this graph to the provider in an accountable way. But it won't reveal information about where, if this sender had actually just been forwarding it on, and this may not be the right person to actually ban because they were just kind of fooled into forwarding things on. You really want to get to the source of these type of forwarding campaigns. And again, here, the end-to-end encryption is going to complicate things because from the provider's perspective, there's this complicated graph of encrypted messages going back and forth between users, and it obfuscates who would actually be sending, this particular message. So what we decided is that we should try to build, we started calling, traceback schemes or message tracing schemes, which are cryptographic mechanisms that help us, help the provider kind of identify the source of messages. And so we had in this paper at CCAE 2019, two constructions. So the first is what we call path traceback, which allows you to, as the name hopefully implies, allows you to trace back just to the first kind of malicious sender in the forwarding chain. Malicious here being someone who either was the original sender of the content or had a hacked client that was kind of deviating from the protocol. And we also looked at how to extend on our path traceback to what we started calling tree traceback, which is in addition to revealing the path back to a sender, original sender, also allowed you to trace forward to see who else ended up receiving this abusive message, which could be useful if you wanted to, I don't know, warn recipients, discover other recipients who might have been affected by some type of misinformation campaign. So again, I'm just going to very high level intuition for our constructions, and I'll just focus on the path traceback scheme. Basically, the idea is when we're going to send a message, we're also going to send to the provider an encrypted kind of pointer to previous information about where this message came from. So if a client forwards a message, then they're going to provide an encrypted pointer to kind of to the previous encrypted information about the previous sender who they had received it from. And under the hood, these are actually pretty fast symmetric encryption kind of mechanisms. In this diagram, we encrypt basically, in this case, if this is the source of the message, just encrypt some error symbol. In the actual construction, this is actually random bits. I just did this for clarity. We also have a PRF using the same key or key drive from K0 of the message contents. And this serves as a kind of a way to do a lookup to find things based on message contents and keys. And for each hop in a forwarding chain, you do one of these encrypted pointers with fresh keys. The keys are actually shared between the sender and the recipient, but not given to the provider at this point. When someone downstream wants to report abuse, they report the message contents, then they also report their final, key for this encrypted pointer abstraction. And this allows the provider now to kind of confirm that this is what they had seen and was associated with this send, and also decrypt the key for the previous hop. And then they can kind of chain backwards to keep going until they finish. One of the tricky things for this was actually formalizing what type of security goals can even be achieved in this setting. And we ended up boiling it down very informally here to a type of accountability goal that we don't want to be able to anyone to be able to frame honest users for committing actions they didn't perform. So framing someone as having sent some is kind of a generalization of sender binding. Receiver binding. And also privacy goals that basically no messages that aren't implicated in a path are revealed to the server, the platform provider. But there's a lot of details that I'll refer you to the paper for. Okay, so in this talk, just give a very kind of lightning quick tour of a bunch of our work over the last few years on trying to build these cryptographic tools for moderation, starting with Facebook's really interesting message franking approach that we then abstracted out the cryptographic goals for this into what we started calling compactly committing authenticated encryption, discovered a vulnerability that we worked with Facebook to help patch on their attachment franking. And then this also spawned a bunch of questions about how do we kind of build these types of tools to work in other kinds of settings, like settings where you have anonymity, or settings where you'd like to do more than just one link of moderation reporting. And I think there's actually lots of interesting questions and future directions. Like one thing that's very near term is that we really need to build standards for committing authenticated encryption. It actually turns out this lack of committing property gives rise to vulnerabilities in a bunch of different settings, not just in this message franking setting. And so we should be targeting standards that are widely available to use. AMF schemes are fast, but you could always ask for them to be faster. There's some interesting variants of the traceback schemes that we didn't know how to build efficient constructions for. So for example, if you just want to reveal the source of a message, but not the intermediate hops along the path, the identities of the intermediate hops, then that seems very hard to do actually, and it's an interesting cryptographic question. And then there's broader questions about how to improve the moderation ecosystem tooling here. One challenge that's very clear is if we're in an end-to-end encrypted setting, how do we help users identify abusive content? Basically, everything I've talked about so far starts from the assumption that the user says, "Oh, this is horrible. I'm going to report this." But even for things like misinformation campaigns, it may not be clear to a user that this is bad content that they should report. In in plain text services, providers can look at content when it's sent and provide warnings to users based on machine learning or other tooling to flag potentially malicious content. But here that's complicated because we don't want to reveal data to the providers. So how do we move some of that infrastructure to the client side in a way that's secure and private? And I think there's a whole host of other challenges, of course, in the moderation space. It's a really big problem that providers are facing. Okay, so with that, I'll stop and be happy to take questions. I think we have some time for questions.